Eric Parker. My call sign is Hellcats, so Eric Hellcats Parker. We'll see why in a second here. I'm a student from SMU way back, and I'm going to speak here today about what I call inventing by design, or the science of innovation. So this is just going to be some notes from the trenches on creating technology and the inventive process. So about me. Well, okay, I put the date in here. Anyway, graduated from SU in 1984. As soon as I graduated, my roommate and I formed a company to make a C compiler for the Macintosh, which had just come out in 1984. So this was a very exciting time. And there was no compilers available for the Macintosh at that time. So we took Mike Bennell's compiler's class project, which was, he wrote a C compiler, and we ported it to the Macintosh computer over the summer and started selling it in October of 1984. Then several years later, I started a video game company called Parsoft and released a bunch of flight simulators, which you can see some pictures of over there. And I joined a nanotechnology company in 1998 and created a software package called the Memulator, which is a solids modeling kernel that's still used in industry today for electronic circuits design. In 2003, I created a system called Digital Molecular Matter, or DMM. And that was used in a Star Wars game, several Star Wars games, and also in the movie industry. And in 2015, I won an Academy Award for the development of DMM. I have some patents, and over the last 6 years, I've been working on surgery simulation, most recently machine learning applications for surgery simulation. And only in the last 3 months, I've been working at a company up in North Dallas on 3D printing. So a lot of different technology. So we'll hear some stories from a lot of these different areas. But first, let's watch some fun stuff to get everyone motivated here. I don't know if you'll hear anything or not. I don't know if people online can hear it. They're very different movies. You've probably recognized some of these. This is from one of the X-Men movies. Whoops. Interesting thing about this shot, once the director saw the final version of this, he asked how much it was going to cost to repair that boat. Of course, it's all digital, so no repairs necessary. Okay, so MPC is the moving picture company, which does special effects for movies industry. And DMM was, they were the first special effects house to pick up DMM, but about 4 or 5 of the big houses picked it up. So it was used, it's still being used. I'm sure it's in over 100 films at this point, but these are just some of the films it was used in. So that's a finite element destruction system is what that is. So it's based on finite elements, but with a lot of technical detail to make it applicable for computer games or for special effects. There I am in 2015 at the Academy Awards, and a couple of hints if you ever find yourself in that same position, try to stand near the center if you want to get on television, right? So you can try to stand near the center. See if you can get anywhere near a celebrity down on the bottom row. That's Margot Robbie on the far left and Miles Teller beside her. On the far right is Larry Hornbeck, who was the inventor of the DLP chip, the Texas Instruments DLP chip, and he got an Oscar that year as well. And smile, that's another key thing. So, but in 2010, who's that sort of stoic looking fellow standing there? That's Mike Bonnell, my old roommate that we started that compiler company. And he graduated 2 years after I did. So that's pretty amazing. 2 roommates from SMU, divergent paths after we did the compiler project, and didn't work together after that. And independently, both did something that got, an Academy Award. So how did that happen? So it's certainly a coincidence, has a lot to do with that, but maybe there's something a little deeper here. So that's what we're going to try to talk about today, is an approach, a philosophy, a mindset that leads to creative thinking and innovation. So part of that is collaboration for sure, because you obviously want to learn as much as you can from others, but also doing things on your own, and exploration, challenging yourself. One of the things that we used to do at the apartment when we were roommates, there's a game called Robot War, where you would basically program in a very simple little assembly language a robot, which had simple sensors. It could send a laser out, detect what was in front of it, it could rotate, it could shoot a weapon, whatever. You'd write this code, you just store it on the computer. It was on an Apple II. Store it on the computer, and it would automatically run one match after another, match after match after match, and build a leaderboard. While you're out in school doing whatever, it's running matches. So you come back and you see how your code was doing. You'd modify it. So you didn't have to be in the same room at the same time. You just would work on your code. And of course, it was a challenge to always try to make your code better than your other roommate. We had 4 roommates at that time. So that was a challenge, a personal challenge. This is something that was every day. So I'm going to try to talk about these sort of patterns and ways of doing things and thinking that lead to, I believe, to innovative and creativity. So this is not about methodologies. So you may have heard of things like TRIZ, of course, brainstorming, thinking outside the box. These are not rules or anything like that. This is just concrete behaviors and mindsets that help you to become a better inventor. So in my opinion, this is all going to be my opinion, this whole talk. Innovation arises from an interplay of mind, awareness, opportunity, and preparation. And so by actively training yourself in these specific ways, you'll be better prepared when opportunity arises. But first, word about technology. What is technology? I consider it the end product of the inventive process. Webster's defines it as, I wish I could see my note, but basically the application of scientific knowledge for practical purposes. And I would say, would you consider the light bulb the application of resistive heating for practical purposes? In other words, did Edison invent the light bulb because he thought, oh, resistive heating, yeah. No, he had a specific application in mind, and he had a specific need, and he had a specific set of skills and talents and understanding that at that moment in time prepared him for taking advantage of that. So I call it the end product of the inventive process. So it's uniquely human. Not many other animals even come close to doing it. Maybe some apes can use a stick and pick out ants from a hole, so they know to use a stick, tool using. But they don't go from there. They don't learn from that. They can make connections. I think that the using of the stick was based on copying behavior. Animals in the wild animals copy. They use copying behavior to to learn more quickly than just always starting afresh. I got born, I got to figure out this whole world. They don't have time for that. So they copy other animals. I think that probably is where that came from. I think humans are unique in that we learn from what we think and what we do. So we both define and are defined by our technology. Like we wear clothes, but we don't have fur. We make tools, so we have general purpose hands. We don't have a specific beak or a specific web feet or anything like that. And we harness energy sources, but we're pretty weak when you compare us to other animals. Like chimpanzees are like 8 times stronger than we are. So in every sense of the word, we are really technological beings. Okay, here's my definition of technology. Technology is the application of ideas to problems. Okay, so technology solves problems. Electricity, medicine, nutrition, sanitation, irrigation. Life expectancy was only 29 years in 1750. By 2015, it increased to 71 years. 90% of the world lived in extreme poverty, defined by an income of less than $1.90 a day in 1820. 90%. By 2016, it was 10%. So, yeah, technology has made a big impact. We are who we are because of technology. But technology also creates problems. So during the Industrial Revolution, many people got jobs, increased standard of living, but it led to poor work conditions and pollution. So demand created opportunities to solve new problems. So more technology. So example, the Green Revolution. So Dr. Norman Borlaug, born in 1914 in Iowa, and he died not far from here in Highland Park in 2009. He lived here in Dallas during the last parts of his years. He used crossbreeding and hybridization, genetic hybridization, to create disease-resistant and hardy varieties of basic wheat, corn, rice. He crossbred with plants that had sturdier stalks or grew taller or denser or grew faster, but were nevertheless still nutritious. Using his seeds, Pakistan doubled grain production between 1965 and 1970. So in 5 years, they doubled grain production. And India increased food production to a rate higher than population growth. So he's a big part of why people don't starve to death any longer, why we went from 90% of low income to just 10%. He received the Nobel Prize in 1970, and economists have credited him with saving the lives of 1 billion people. You could do worse. The increased yields, however, required less land devoted to agriculture, was a good thing, but the popularity has led to reduction in genetic diversity. So that's a bit of a problem. So we want genetic diversity because, well, diversity is good in many ways, but for genetic variety, it's very important so that you don't end up with too much crossbreeding and reduction in evolutionary sort of trial and error. So inventing. I call inventing the creative process of coming up with technological ideas to solve problems. So it is really at the heart of the human project, right? I mean, it's who we are. Future technologies will help solve today's seemingly insurmountable problems. I mean, global warming comes to mind. The answers usually seem very obvious in hindsight. And it's critically important that as a species, we succeed. The world needs innovators. So let's look more closely here. Mind models. Now I've got whoops. Oh, let's see if I can pull this over here. I got a prop here for this. Okay. So I like to talk about mind models. So I've got this handful of Lego bricks here. So this is Emmett's brain. Did you all see the Lego movie? All right. It's just an endless expanse of nothing. But information spontaneously appears from his senses. Try reading a sign, or looking at, I should say read it. Try looking at a sign, a billboard, and not reading it. You cannot. You cannot just look at the letters and say, oh, there's a weird shape. No, you see a word. It's spontaneous. Our senses deliver information into our brains spontaneously without our thinking or doing anything. No understanding. just raw data. Things just appear in our brains. Knowledge, however, is constructed from this information and ideas. So I'm drawing pictures of ideas in yellow there. And understanding is finding relationships between ideas and other ideas or information. And so I'm drawing understanding as these green connections. So you have information which just arrives without you thinking about it. Then you look at that information and you start to put it together. So you start constructing something. Like here's these pieces of information floating around and you get an idea. So you connect things together here. And maybe you make some kind of a, who knows, a thing. Okay, but that's your idea. All right, that's your knowledge because you've taken information and other ideas and connected them together and formed some understanding. So you take that model, that mind model, and you put it on the shelf. Okay, and you go off and do something else. And it just sits there because you aren't thinking about it anymore. But you might come across something that's related to that. So you pick it back up and you plug something else into it. And in fact, anytime you're not doing anything or have nothing better to do, you might as well pick up one of your mind models and improve on it because you can always make it better, right? So understanding and knowledge isn't just something that you go to school, take the class, you write it down, you're done. It's something that you're constantly improving, you're constantly finding relations to other pieces of knowledge or other pieces of information, improving your understanding, and you're trying to make these models, these mind models, as general purpose, as practical and applicable to as many areas as you can, and try to constantly be improving them. And it's one of the things I found that's very useful is to go back to the basics. If you have gotten all the way through calculus and you feel like you really got that down, go back and read chapter 1, just the intro. You will learn so much more having gone through it once. You will pick up a huge amount. And you think, well, why should I go back to the basics? I find myself doing that all the time. You know, I've programmed in C++ since it was invented, but I still go back and learn new technology or new skills from watching simple videos on intro C++. It's amazing. Yeah. Recognizing patterns, filling misses. Yeah. Okay. Knowledge versus information. So knowledge, in my definition, is information that has been transformed by a process that I like to call thinking. You may have heard of it. So it's information, raw information, and you've transformed it into knowledge. Knowledge is created entirely inside the mind. It cannot be placed there by an external agent. Your professor cannot place knowledge into your head. It is your creation, okay? It is private, it is personal. All learning is a creative act. You must create it within your mind. Someone is writing out all the steps for doing L'Hopital's rule, whatever, and you just write it all down. But you're not creating knowledge from that. You're not producing knowledge unless you are creating it in your mind, okay? So you're thinking about it and trying to say, does that make sense to me, okay? That's how knowledge is created. It's created. So everyone has a different set of mind models, depending on how they learn things, what knowledge they produced. And it's private, it's personal. So you should try to visualize, what have I got in my head? What have I filled my head with? You know, are these contraptions I have, do they make sense? Can I improve upon them? Can I take them off the shelf and look at them and play with them and improve them? So the accumulation of knowledge, it's incremental, it's nonlinear. New knowledge leads to insights about existing knowledge. And your intuition, once you've gained a lot of knowledge, a lot of experience in a field, your intuition is based on that knowledge. So better knowledge equals better intuition. So keep revisiting and examining what you know from all sides, pick it up off the shelf, look at it again from a different point of view. And anything that improves the model, including finding flaws, is good, right? Oh, that's a mistake. I should not have done that. But I just improved my model, okay? So that's actually useful. I shouldn't feel like, oh, that was stupid. I should never have done that. So admitting error and admitting mistake is a way to optimize. It's a step towards improvement. There's no such thing as the perfect model. It can always be improved. So don't feel bad about improving something or finding an error in your way of thinking or admitting to it, because you're making it better. So always seek out answers to questions. Don't leave something that you don't understand, like, oh, I just don't get that. I feel so embarrassed if I say something or raise my hand. Don't feel bad about that, because that's how you make a better model. And that's what we're all here for. So sort of a motivating slide here, cultivate your mind. The patterns of knowledge you create over a lifetime, they really are your greatest treasure. And as an engineer, you will directly impact the lives of everyone else with your ideas and abilities. 1% of human race is engineers, right, and inventors. 99% are relying on the results of that engineering and that technology. The mRNA vaccines were developed by just a handful of people, but look at the benefit of it. Dr. Borag with his hybridized plants impacted 1 billion people, just one guy. So we really are, as engineers, you guys are really at the leading edge of what is good about society and about even the whole continuation of the human race, because we are technological. So actively work to grow your mind by thinking, reading, experimenting, engaging with others. It's a nice quote from 2001: A Space Odyssey by a computer named Hal.
I am putting myself to the fullest possible use, which is all I think that any conscious entity can ever hope to do.
So I like that quote. He's putting himself to the fullest possible use. What else can you ask for? So the inventive process. An invention is just an idea that solves a problem, and ideas are constructed incrementally from prior knowledge and information through intuition and thinking. For the inventor, a great invention could be as simple as just creating a link between two pre-existing mind models. Two ideas that you just have, knowledge that you've had, you explored from every angle, and all of a sudden you put a link between them. New understanding. And boom, it's an aha moment. Something amazing happens, right? To us, it may seem miraculous, but to the inventor, it was obvious. It's like, oh, just this and this, right? It's only because he had that set of models and understanding built in. So success definitely favors the prepared in this regard. You don't just walk down the street and all of a sudden figure out mRNA vaccines, right? You have to be prepared for that. So how best to prepare? That's the key question. Too bad there's no silver bullet for that, right? Or is there? Anyone want to hazard a guess what the next slide might be about? The silver bullet for being prepared to innovate and have those aha moments. There really is one. It's a key in the title of my talk. It's the scientific method. So boring, right? Okay, well, it really is one of humanity's greatest inventions. And it's not just for scientists, okay? You can apply it in your daily life. You can live and breathe the scientific method, okay? And use it to cultivate a rich and supremely capable mind. So here's some examples. You're taking a class. The observation, right? Observation, hypothesis, experimentation, analysis, right? That's the scientific method. So the observations, you read the syllabus, find out what this class is about. You read ahead in the chapter, okay? The hypothesis, predict what the professor will say at the next meeting. Don't wait till you get there. Actively predict before you get there. Make it an experiment. Then listen, compare what he's saying, he or she, and check your alignment with your prediction. Where did you make a mistake? Take the notes with regards to that. Don't just take notes like a stenographer, okay? You're just taking notes, everything that's said. You're not learning anything. You're just a recording machine, right? No, compare what's being said to what you predicted, correct or update your understanding, talk to other students, ask questions, and then iterate. The scientific method is got repeat in it. You go back and you keep doing it. It doesn't tell you, it doesn't make perfection. All the scientific method does is improve on what you already have, okay? So it's about a constant updating and a constant comparison and learning, constant learning, lifelong learning, definitely. But lifelong learning with a methodology, and the scientific method is the methodology for lifelong learning. And you just be self-aware about it. You think to yourself, I've met someone, seems to really know a lot. I would like to acquire their mind models. Okay, so they've got some beautiful mind models. I wish I had them, okay? So you tell them, what is my understanding of what you know? Listen to what they say, compare with what they say with what you predicted that they would say, okay? And then update your knowledge and cycle back around. Reiterate, I think my understanding, is this now correct? You've updated your model and you say, well, you added this little piece here, and you ask them, is this what you mean? And you listen again. And that iteration, that iterative cycle, is how you could then acquire at least some rough inkling of their mind model. And then you can go take that and plug it into your knowledge base. Okay. And in inventing, really the key is curiosity. I can't tell you how many times in my career, just having played with something or explored something on my own, created a little application, made a little game, the curiosity, investigation, reading without a particular need or necessity, later, even sometimes 20 years later, or even 40 years later, has come back and said, oh, I remember that. And you don't have to know it precisely, but you just have to be aware of it. So you can go back and research it again and see how it applies to what you're doing now. So curiosity is really key to the inventive process. All these other techniques, of course, were useful to become a good engineer, but if you want to be a good inventor, I think curiosity is really necessary. And so again, modeling, framing relationships to prior knowledge, then experimentation, prototyping, play with your ideas, because during that play process, you will learn what does and doesn't work, and then you'll update your models. So collaboration, I mean, you can't do it all yourself, right? So one of the fastest ways to build more models is to work with others, discuss ideas, get feedback, offer suggestions. But I want to give you a warning, be very careful of group dynamics. You get into a group and it's easy to become reliant on others to take the lead and not really do any thinking of your own. Really, collaboration works best after you've spent time on your own trying to solve the problem and struggling and developing your own ideas first, okay? Draw your own conclusions without deferring to authority. Then come together and compare notes and learn from others and update your ideas, and then go back and work independently again. So that going away, working independently, coming back together, exchanging ideas and knowledge is going to be very efficient because you've worked independently. You all have a shared genre, jargon, I should say, a shared jargon, a shared knowledge and understanding. And anything that you've missed, someone else fills in that gap. Then you go back apart again to work independently. That is the way to make collaboration work. So always try to build the strongest analytical skills of your own. So now we'll do some examples from my career and look at some of these, how some of these ideas sort of played out. So the first one is this Hellcats over the Pacific flight simulator, released it in 1991. It started with what you would call an aha moment. This is where I connected two mind models. One was this polygon, how to do polygon rendering. So how to turn, or it's called rasterization, to turn triangles or polygons into pixels on a screen. So it's essentially a mathematical, slope problem. You're basically computing the change in y with each change in x, and then rounding that to an integer, and that's a pixel. And you walk down these edges doing that. And one evening, I was playing with this new supercomputer at the time called a Spark Station. It could run 20 MIPS, 20 million instructions per second, which is, a light switch is faster than that today. It had a 1 million pixel display of 8 bits each. So that was 1 million bytes, so 1,000 by 1,000 display. And the memory bandwidth of the CPU was 40 megabytes a second, but it had no GPU. This is just a dumb CPU and RAM, which was mapped to the screen. But the screen was mapped at only 5 to 6 megabytes a second. So if you wrote data to the memory that was drawn on the screen, the pixels on the screen, you could only clear the screen with a new value every 5 or 6 times a second, which clearly wasn't fast enough to do any kind of 3D modeling. I knew how to draw polygons, but I also knew this was way too slow. Okay, so a fast CPU, fast RAM, but slow graphics. It was like, oh, I can't do 3D graphics. The accepted wisdom at the time was to optimize your code so that you maximally utilize your memory bandwidth, which in this case is only 5 or 6 megabytes a second, which would be easy to optimize to maximize that bandwidth. But this 20-minute processor would just be idling like 90% of the time. It could write 40 megabytes a second, but the graphics could only go up 5. So most of the time it's just idling. It seemed extravagant. It was an affront to my hacker sensibilities. So I wondered, could I be less efficient with the CPU? Don't ram as many pixels as you can per second, but be smarter about it, smarter about the rasterization. And instantly that forged a link between polygon rasterization mind model and image compression mind models. How does image compression work? So the idea was to modify the polygon rasterization to render a compressed version of the triangles, not every pixel, but where's the start pixel and offset, and how many pixels? So it's just two numbers. Where is it? How far long is it? Next edge, where is it? How long is it? Okay, so that's all you're rendering. You're not actually rendering the pixels themselves. And then compare that version, this frame, with the previous frame's version. It has an edge position and a length. It has an edge position and a length. Compare those two, see how many pixels are different, and only draw that to the screen on each frame. So what was on the screen the previous frame is still there, and then you undraw parts of it and redraw other parts. So you're drawing little slivers. You're not drawing the whole screen every single frame. And in fact, the less that changes per frame, then the faster you can draw, the less you have to draw. If less changes, so the faster you draw, the faster the frame rate, the less it changes, and the less you have to draw, which means the faster the frame rate. So it's a positive feedback loop. Okay. So I was so excited. In 78 hours, I coded it up, and I had a full screen cube, 3D cube, rotating at about 120 frames a second on this computer that only could do 5 frames per second. Okay. So what am I going to do with it? You know, Spark Workstation, no one's going to pay anything for that. But the Macintosh was out at that time. The color Macintosh had a 640 by 40 or larger display. You could buy graphics cards. So it took about a year to create this Hellcats over the Pacific flight simulator game. Later, I created a series. Won a couple awards for those. And texture map GPUs ended the market advantage after about 5 years. So there was a window, technological window, and this is totally true of all technology. There's a leading edge when the technology becomes the greatest new thing. There's a period of time when it's applicable, and then there's an obsolescence. And all technologies are a moving window of ramping up, being valid, and then obsolescence. And something else comes along that replaces it. So this is a feature of technology. And again, this is why lifelong learning is important, because what you know today will become obsolete eventually. So here we go. Here is Hellcats over the Pacific from 1991. It's a bit cartoony looking today, of course, but this was considered state of the art in 1991. All software. All right, won't go too much further than that. All right, another case study. This is now getting into nanotechnology. I was working at a company called Zyvex and Richardson that was trying to research nanotechnology. The idea being that you could try to manipulate molecules to build little robots at the molecular level. And one of the things we wanted to try to do was mimic some of the ways that bacteria or viruses that are able to just explode in numbers, but they're extremely small molecular machines, basically. Like a virus is just a molecular machine. So we wanted to try to see if we could mimic that with a technological approach, a chemical approach, try to build molecules. Well, that's a big step to take. So we decided to try a proof of concept using a mesoscale as opposed to a nanoscale, or micro scale versus a nanoscale. And some of the examples you get here, very low precision relative to the size of the parts are very, very small, but they're very low precision. So it's sort of like trying to build a log cabin with boxing gloves on. All right, it's like you're picking up these logs, but you have really no way of gripping anything other than just like pushing on it, and it twists, and you're trying to build things with boxing gloves. That's really what nanotechnology is like. You have to rely on energy minimization, setting up the conditions so that the system sort of snaps together by itself, like magnets in a box. You just kind of get in near the box and shake a little bit, and all the magnets sort of snap together. That's the way you have to think when you're trying to design nanotechnology. So we came up with this idea that is called exponential assembly. And it's using MEMS, which are microelectromechanical systems, which are basically integrated circuit technology, but made mechanical. So you etch away part of the layers. And the key insight was that there are basically 6 degrees of freedom, right? There's 3 translation, X, Y, Z, and rotation about the 3 axes. But translation can be shared by multiple parts. You put a bunch of parts on the table, you move the whole table, they're all translating. But they can't share rotation, because the rotation depends on the radius, how far out from the center you are where you're rotating. So they all can't share the same rotation, but they can share the same translation. So let's do that. Let's put all the parts, all the robots on a table, move the whole table around, and then they only have to provide the rotation independently. So here's a little animation showing how we set up with an external, these are our robots here built out of a flat layer using integrated circuit technology. So we have an external robot with a little tweezer on the end, okay? And what it's going to do, it's going to come down, and remember this is at like, 20, 50 micron scale, something like that, these parts. So it's going to come down, it's going to pick up one robot arm, turn it 90 degrees, and stick it in another robot. At that point, we call that a rotopod. That is a fully assembled robot. We only have to do one, okay? After that, we then take two wafers of rotopods and set them up over each other. And they're mirror images. So the same set of commands is sent to all the rotopods for rotation, but the table itself provides the translation. And so now you get a doubling. Every time you run through the process, you start with 2, then 4, then 8, then 16, and it exponentially increases the number of rotopods. Okay. After that, you have a whole wafer of rotopods. You only have to assemble one by hand. And then after log n base 2 sets of operations, you end up with 2 to the n. So you get exponential growth. And then you have a whole wafer of these rotopods that you might be able to go stick on something to do something. You lower it down on something and it picks up all the dirt. So like mega vacuum, it picks them all up by piece. Who knows? Okay, so that was interesting. Digital molecular matter. Okay, so we'll talk about that. This is a little different. This really wasn't just an idea. This was combining existing technology, existing ideas from papers. So these were sort of the 3 papers that led me to develop DMM. One is on integrated a time stepping method, implicit time stepping. Another one is an efficient way of calculating fracture in finite element methods. And the third one was a way to deal with nonlinearity in finite element method. Finite element method typically, you can solve it with a linear system equation, but then if you try to do a large displacement, you get all kinds of distortion and error. So that becomes a nonlinear problem. So how do you efficiently handle nonlinearity? And this paper describes what's called the co-rotational method for doing that. So I kind of realized those 3. And again, that's just from being curious, just reading widely without any direct application. But just combining those 3 sounds easy, but there's a lot of technology to get that to work. So some of the problems, newly fractured surfaces, when things crack and break open, they're immediately coplanar. Like you have a box, you cut it in half, nothing's moved yet. Those 2 surfaces now are exactly coplanar. That is a degeneracy if you're talking about collision detection. So immediately you've got a problem there. You're going to have all kinds of problems if you just use a standard surface-based collision detection system. So we came up with volumetric collision detection. You need real-time performance. You have to have predictable performance in a computer game. You can't have it go along fine. All of a sudden, it takes 5 minutes to run through this frame. Now we're back up to high speed again. It's got to be predictable. So we only did fracture at nodes, not any arbitrary locations within the structure. And then we used a solver which had linear scaling. So then we could get a predictable performance. But we wanted to have really high resolution fracture. But the simulation mesh could be low resolution. So kind of over here in the corner, you can see where you have these triangles, which are your finite element mesh, that's where the simulation occurs. But then you have these pieces of geometry that jut out and can be very, very detailed. And we call those splinters. And the splinters are attached wherever their centroid is, to whatever finite element mesh they're inside of. But as the finite element mesh distorts and turns, then the splinters come along for the ride. Okay, so it looks visually like there's a huge amount more detail than there really is in terms of what's being computed. And then the last thing, it had to be arc directable. Oh, it also had to be robust, never crash. The Star Wars Force Unleashed games sold over 7 million copies. It was the fastest selling game, Star Wars game in history. And they really didn't want a lot of them returned because they were crashing. So it was very important that this finite element simulation always worked. And was deterministic. So determinism was one of the keys to making it work, because if it was deterministic and someone reported a problem during testing, we could reproduce that problem. We could set up the initial conditions and simulate the exact simulation that occurred when they described the problem. So every single problem that was reported, we tracked down the root cause and fixed it. There was never a report that we couldn't replicate because we had full determinism. And then it had to be art directable. You had to have all these artists creating this stuff who didn't know anything about finite element simulation. So here's some footage from the Xbox 360 version. Here you can see the splinters. In that case, it was wood, so his splinters. Causing some pain for that Wookiee there. Okay. And this is just showing, again, the splinters. You see the bricks sticking out. And here you can see the finite element triangles or tetrahedra, where the actual simulation occurs, and you can see the bricks kind of stick out. This is an example from Star Wars, and this is changing material properties. This is making a tougher wood that doesn't splinter as easily. Same exact mesh, but now with a different set of material properties. And this is showing editing of material properties. So you can go in and change Young's modulus, and then just reset the simulation back where it was and rerun it. So now it's a little less stiff. Now we're going to lower dampening. So now it's a lot more rubbery and wobbly. It's still fracturing a little bit, as you can see there. And what are we going to do now? I'm going to further reduce Young's modulus. Now it's basically a sheet of rubber. All right, so James O'Brien, who's the author of one of those 3 papers, we consulted with him, and he and I wrote a paper together for SIGGRAPH, SCA in 2009, publishing how we did all that. And then Ben Cole from MPC saw the paper, our presentation, and he contacted us because he was looking for a new technology for doing destruction in the movie industry, special effects industry. So he took DMM and installed it within his system called Kali at MPC, and made all these movies. And the other movie houses saw that they were having a lot more ease in creating destruction, so they wanted to license DMM as well. So like I said, 4 or 5 of the major special effects houses licensed it. And so I'm sure it's been used in over 100 films easily at this point. So the 3 of us shared that technical award. So the summary, common features: identifying an opportunity or problem, proposing a solution based on prior knowledge, trying out the idea, prototyping, and then going back to step 1, refining, or step 2 at least, refining and improving that scientific method. Here we go again, right? So step 2 is kind of where the magic happens, proposing a new solution based on prior knowledge. Okay, so the only way that I know to do that is to prepare by cultivating these deep mind models and spending every day on that and making it proactive, being explicit. I want to make my mind models better. I want to learn your mind models. Don't just let it happen and just, just think I need to do better. Make it explicit. It's a set of rules. And in fact, I brought you guys some gifts. I'm gonna hand those out. So I gave you a little card for your fridge to remind you to use the scientific method. So pull at the threads. Don't just memorize. Revisit, revise, be curious. Curiosity for innovation, I think, is really key. Apply the scientific method every day. Collaborate and communicate with your peers. And finally, think. And so you guys, you young people are now the vanguard of human progress. Okay, we're dependent on you guys. All right. So I'm passing you guys the torch. And because of that, it really has been an honor to be here with you guys today. So thank you, and pony up. Any questions? I'll certainly take questions at this point. Yes.
I saw that I think you're working on a machine learning application for surgery. Could you talk a little bit more about that and maybe how you kind of factored in machine learning into that?
Yeah, so the application was auto extraction of vascular structure from CT scans or MRI. So just a raw CT or MRI, and you want to auto extract all the blood vessels, the vascular system. but not the bone. You just want the blood vessels. So I tried several approaches because again, there's no tried and true solution. The first thing you do is you read all the papers. You just go read what other people have done. And there's a lot of good ideas out there. A key problem though was the application. This was for endovascular surgery. So the company I was working for built simulators for endovascular surgery. So they have a physics simulation of wires going through the blood vessels. It's real time, and basically they have a device that's more or less like a set of 3 mice, computer mice. You can stick wires in it and twist them, and they can be coaxial. It can handle up to 3 coaxial catheters and wires. And then as you push the wires and the catheters in and twist them, it reads how far you're pushing and how much you've twisted. And then it shows on the simulated fluoroscope the motion of the wire through the blood vessels. So it was important that the blood vessels that were extracted be smooth, because you've got a simulation running through it. You don't want it catching on holes, or you don't want to have a triangle mesh that doesn't fit tightly. And because it was extracted automatically from a CT scan, you can have a lot of noise. And so you don't want to have a hole or a gap. You're pushing the wire, and then all of a sudden it's just over the brain somewhere, or it's up in the collarbone because there was a hole. It's not really there. Or worse, it's blocked off and you're pushing, and all of a sudden it's coiling up over here, and so prolapsing, and it's like, well, why is that happening? That shouldn't be happening. So it was critical that the blood vessels meet the criteria of being continuous and smooth, regardless of whether or not it was a truly accurate extraction of those blood vessels. So that required it to be a little bit different. And the technique I first started with a GAN-based method. And a big problem, of course, is just generating data. I mean, it's really hard to come across medical data that you can use for experimentation because of privacy concerns. So I started by using a GAN to auto-generate pseudo CT scans. So I made up CT scans by training a GAN to create virtual CT scan or synthetic CT scans that were in the same distribution as real CT scans. So I trained it on the real CT scans and used that to train the GAN to make synthetic ones, and then tried to use the synthetic ones to train a model to construct synthetic ones using a model of a blood vessel. So a model of blood vessel would be a wire with varying radius rendered as a spline. Okay, that would be your mathematical model. And so you try to incorporate that into the GAN as part of its construction of the synthetic CT. So it's trying to construct the synthetic CT, not just from randomness, but from randomness applied to a mathematical model from which we can extract smoothness and continuity guarantees, right? That didn't work out so good. It was working more or less, but it wasn't achieving the results that we wanted. So I went down a completely different route, where I took the simulator, the physics simulator of the wire, and put it on a real CT, and then using inverse rendering, rendered just the area around the tip of the wire, optimized by optimization. So basically I have a rendering process that is trying to match the CT, okay? And that then, once rendered, applies a force to the wire, and the wire moves. And as the wire moves into the vessel, it sort of snaps. It's like a phase lock loop. It's like a feedback loop. So the rendering of the blood vessel is trying to match the CT. Okay, but the vessel is a spline, right? And it's physics-based. It resists bending. Okay, so the rendering rasterization of the CT, the synthetic CT, which is inverse rendered, it's inverse rendered through that wire model. Again, similar to that wire model concept, but instead of training with GAN, we're now trying to have it match the blood vessels that it's sitting inside the CT. Then you only have to deal with just the region around the wire itself. It's based on our simulator, so we know it'll be able to navigate because it's what's extracting the blood vessel. And then you just push the wire using the simulator. And so it pushes along, and as it pushes along, it has to render and rasterize around the wire to match the CT. And where there's an error, it creates a force on the wire. It pushes it back into the blood vessel. So it's a feedback loop. So the closer it gets to rendering properly, the better it does. And that works actually pretty well. So, and it's very fast because it doesn't deal with the whole CT at a time. It's only dealing with small snapshots of it.
Great, thank you. That's really interesting that you got to use, since like no data is available, you render out your own image.
Right. Using a GAN, for instance, to build synthetic CTs. Yeah.
I'm a data science major, and I've never heard of that before.
Well, you hear it her first. Heard it her first. Any other questions? That's a good question, by the way. Yeah. Oh, I can't see those. I'll go around this way. Yeah, let me get back over to yeah, okay, chat questions. All right, here we go. No, I don't see it. Look, I'll just come over here and see it. All right. What was the biggest challenge you have encountered with inventing something, and how did you approach it? Well, I've certainly had a lot of sleepless nights, and I would say probably during the building of DMM. And I guess I could show you a little video. Let me see if I have it here. No, I don't see it here. But so there was a video of some early work I did of the destruction system that was shown to George Lucas. And the reason is because Peter Hirschman, who was the vice president of software development at LucasArts at that time, who was working on the Star Wars game, when he was in high school, he used to play Hellcats. So when he found out I'd made this simulation, he was all like, I got to see this. So that was my in, right? It's really hard to just knock on the door at LucasArts or Lucasfilm and say, hey, I got something I want to show you. You know, they're not going to listen to you. So I got lucky in that regards. But again, luck favors the prepared. But anyway, this little video showed a castle being destroyed by boulders thrown at it. And so he showed that to George Lucas. And so that's how we kind of got into the project. And at one point, Star Wars and an Indiana Jones game were both being developed based on DMM technology. And there was probably 250, 300 developers, all told, artists, everyone. You know, this was like a $200 million project to build these games. And all of it relied on DMM. And at the time, I wasn't sure how I was going to do collision detection. And I can remember sitting at my keyboard and sweat literally dripping off my nose as I was like under huge pressure to figure that one out. And finally came up with this velocity-based approach, which only dissipates energy, right? So when things come into contact, all they do is slow down the velocity. They don't push back. They don't produce any kind of penalty force. And so therefore, you're guaranteed that this thing's not going to blow up. It's not going to add energy to the system, which could then cause things. We're talking about destruction, where things are banging into each other at high speed and overlapping and huge amount of mess going on. You don't want parts of that to numerically explode. And so the collision detection that used dampening forces only would end up with interpenetration, yes. But when things are flying around at high speed and things are blowing up everywhere and there's smoke and fire, a little bit of interpenetration, you can forgive that, right? So yeah. So that was probably the most challenging, or at least the most stressful inventive problem that I ever had, because everyone was writing on it. And then people would tell me, this one technical director told me, like, wow, do you know how many people's livelihoods depend on you? It's like, man, don't tell me that, Yeah. All right, great. Well, that was a lot of fun, guys. So thank you for inviting me, Cassie, and everyone else who participated. So if there's no other questions. All right, thank you.